Hi, I'm Tom Nahomi from Dell EMC. This video will show the steps involved in deploying a fully functional Tanzu Kubernetes Grid cluster via vSphere with Tanzu and Dell EMC PowerMax vVols. Virtual volume was introduced in vSphere 6. This is a storage technology that provides policy-based granular storage configuration and control of virtual machines through API-based interaction with the underlying array. vVol benefits include virtual disk granularity, automatic provisioning, array-level VM visibility, storage policy-based management, and more. Starting from PowerMax version 9.2, the array comes, when ordered, with embedded VASA already installed and configured. There is nothing to configure or deploy for VASA 3. By navigating to the vVol dashboard, we can review and configure our virtual volumes. Here, we can create new storage containers and configure the masking between the E6A hosts and the PowerMax array. In the latest PowerMax patch, 9.2.1.2, the embedded VASA is now available for post-install implementation on PowerMax array if it was not requested when ordered. As you can see, there are two instances of the VASA 3 provider for high availability. Both providers are registered in the vCenter server with run recognized as primary and the other one as standby. Now, let's navigate to the vSphere client. In the vSphere client inventory pane host and cluster, we select the vCenter, click on configure, and then on the storage providers in the menu. As we can see, the PowerMax VASA provider is registered with the vCenter. To view the protocol endpoint presented to a host, we click on the host, select the Configure tab, and select the protocol endpoint from the menu. Here, we can see the PE properties, paths to the storage array, and vVol data stores. If we navigate to the data store pane, we can see that the vVol data store is mounted on the E6A hosts. The first thing we need to do is building a storage policy in vSphere that can be referenced by the Kubernetes storage class manifest. When provisioning volumes with the CNS, the VMware CSI driver, we are going to use SPBM. SPBM is a great model for FCD because for vVols, it allows us to assign any array capability we want to the volume to have, independent of the VM it may be associated with. For instance, on the PowerMax array, we can set the service level, quality of service, for the volume. PowerMax vVols leverage storage policy-based management to ensure virtual machines have the appropriate storage capabilities through their entire life cycle. VM storage policies can be optionally created after the storage provider is registered. These policies are used to determine the desired storage capability when a persistent volume is being provisioned. To create a storage policy, we navigate to the VM Storage Policies page in vSphere and click on Create VM Storage Policy. Here, we provide it a name and click Next. Then, we check the box Enable Rules for vMax vVol Provider Storage. These rules are automatically created during the PowerMax VASA registration. Here, we select the service level. PowerMax QoS priority rule determines the relative performance prioritization for that vVol. Here, you can see that our vVol data store is compatible with the storage policy. Now, we click Next and Finish to finish the policy creation. vSphere with Tanzu is the new generation of vSphere for containerized application. As of vSphere 7 Update 1, customers can run pods directly on the E6A hosts, the supervisor cluster, and also inside virtual guest cluster running Photon OS. These pods consume storage via the VMware CNS. While both VMFS and vVols are supported, in this demo, we will be focusing on vVols, which are preferred as the storage of choice for container volumes because of scaling capability and day 2 operations. In order to deploy the Tanzu Kubernetes Grid cluster, we navigate to the Workload Management tab and then click on the Namespace tab. Here, we click on Create a new namespace. We select our supervisor cluster, specify a name, and click Create. We can see that the namespace creation completed successfully, and the Kubernetes status is active. At this stage, I'm adding permissions to the vSphere administrator user to manage this namespace and adding the Dell EMC PowerMax storage policy I've just created to our namespace. This will allow us to create TKG persistent volumes on my Dell EMC PowerMax vVols data store. Next, I'm logging in to my vSphere supervisor cluster using the kubectl command. I'm specifying the supervisor API address, the vSphere user, and password. Then, I'm switching to my new namespace I've just created using the kubectl config useContext command. By running the kubectl guest sc command, we can see the PowerMax policy. This appears as a storage class within the namespace. As you can see, I'm using the PowerMax storage class in my manifest file of my TKG cluster. This storage class is used for both the control plane and the worker nodes. For the purpose of this demo, I'm about to create a single master and 3 worker Kubernetes 118 cluster. I'm going to create it so we can go back to the vSphere UI and see what's actually happening in our namespace. We can see that a new TKG cluster object has been created and the control plane VM has been built out but hasn't been powered on yet. I'll speed up things a little bit as this process takes about 10 minutes to complete. As you can see, the TKG cluster is up and running. By clicking on one of the virtual machines, we can see that they are actually running on the vVols data store. Now, let's log in to the guest TKG cluster I've just created by specifying the Tanzu Kubernetes cluster name and the namespace. The PowerMax storage class is attached to this TKG as well. This will allow us to create vVols-backed persistent volumes for our cloud-native applications. We can take a look at the nodes to make sure we are in the right context. Here we can see the single control plane and the 3 worker nodes. Now, let's create a stateful application inside the TKG cluster. For the purpose of this demo, I'm deploying an application called Yuga by DB, which consists of 3 master nodes and 3 worker nodes. Each has a persistent volume claim, which will represent a single virtual volume. By navigating to the vSphere UI, we can see that the CNS driver is creating the virtual volumes on the PowerMax array, attaching them to the Tanzu worker nodes, and mounting the persistent volumes on the pod so the database can access it and start the pods. Within a few seconds, all the persistent volume claims are running and bound to the pods. Using the kubectl commands, we can get information about the persistent volume claims, persistent volumes, and the pods themselves. Now, let's connect to the PowerMax cluster and navigate to the VMware tab. By clicking on one of my ESXi hosts, we can get a list of my virtual machines running on these hosts. If I select one of my TKG VMs, we can see that we have multiple virtual volumes, and each and every one of them represents a single Kubernetes persistent volumes of my cloud-native database. Persistent storage is presented through the VMware CSI driver called CNS. CNS uses existing storage options for storage provisioning in a new way. First, it is based on storage policies, as we saw, and it uses first-class disks instead of standard disks. FCDs are just virtual disks, But in the API, there are first-class objects. They can be created and exist independently of a virtual machine, which makes sense for something like a container. FCDs can be created, snapshotted, resized, etc., just like a virtual disk, but without a virtual machine to own it. This is exactly what Kubernetes persistent volume claim is. One of the main advantages of running Kubernetes on top of vSphere is the insight we receive via CNS. Rather than having to keep switching between arrays view and data store content view, we can view all the information of the persistent volumes consuming vSphere storage in one place. Under the container volumes view, we can see very useful information about the persistent volumes managed by the CNS driver. We can see the PV name, the vVols data store, which is compliant with the storage policy, and also the health status and the capacity. Under the basic view, there is more information such as the type of the volume, the storage policy, and the volume ID. We can see even more information about the Kubernetes object, such as the different labels, the name of the pod, and the namespace. Dell EMC PowerMax vVols integration is a key component of this solution, as it offers full flexibility and granularity that may be required by your containerized application. You can define multiple VM storage policies which can be assigned to different storage classes within Kubernetes to really fit your needs. I really hope you find this demo useful, and thank you very much for watching.